Hey guys, and welcome back to another video in my series of university physics videos. It has been a while since I've done the last one. I think in the meantime I've actually finished my physics degree, so hopefully I'll have a bit more time to devote to these. For now I'm going to carry on doing statistical physics, but I do plan on doing things in quantum physics, condensed matter physics, and maybe some other more niche areas of physics like atmospheric physics and biophysics, but that's a long way off. So I'm going to carry on with statistical physics, as I know that's probably the most requested area of physics that is around. So far on my playlist, we've mostly focused on a lot of classical statistical physics, so like analysing microstates and macrostates, and going from statistical, sort of bridging the gap from statistical to thermal physics, which is good because it shows that statistical physics is a good theory and can lead to thermal physics. But statistical physics can actually go a bit beyond what it does in the classical world, and you can actually use a lot of pretty powerful tools like the partition function, like we mentioned, to not only predict classical physics behaviour, but also predict quantum mechanical behaviour. And this is some really cool stuff. Like, you can get things that are pretty unintuitive, like superfluids, and you can get some really interesting magnetism effects. And this is all originally from the assumptions of statistical physics and taking the whole statistical physics approach by using tools like the partition function and the density of states. So this is all stuff to come. I'm actually going to be starting off by introducing quantum gases. That'll be mostly the topic for this video, is introducing quantum gases. And from quantum gases and some of the kind of basic key assumptions we make about quantum gases that come from quantum mechanics and things like the Pauli exclusion principle, we actually get some quite interesting statistics that are quite different from the classical statistics that we're used to with the ideal gas. And basically you get, lots of really funky things like degenerate matter and things that kind of really behave very differently on a macroscopic scale just because of things like the Pauli exclusion principle. So without further ado, we're going to jump right in and we're going to see how statistical physics can be used in quantum gases. Now, I'm not actually sure if I mentioned this in my other videos, but you can get a lot of the ideal gas formulas from taking approximations and limiting factors. Now, an ideal gas is basically assumed to be what's known as dilute. Now, what do we mean by dilute? Dilute's a kind of general term. What do we mean in this exact context? Well, dilute basically means that it is super unlikely for any two particles within this gas. So let's draw out our familiar box of gas that we have. Here's our cube. I won't give it dimensions quite yet. And it's going to have lots of gas particles floating around. They're going to be whizzing around. Now, what a dilute gas is basically a gas in which none of these particles have exactly the same quantum state. So you know how in the density of states video I talked about sort of this idea of filling up this ladder essentially of quantum states. So you have, maybe one level at this energy, two levels at this energy, three levels at this energy, and so on. I mean, this is unique to the system. It's determined by properties such as the dimensions of the system and also the mass of the individual particles. So this is what the density of states is kind of measuring. So there's like maybe our density of states curve right there, rho of epsilon, where epsilon is the individual particle energy. In a dilute gas, it is so unlikely that any two particles will be on the same energy level. It's like, even including spin, there is no way that two particles are going to be on the same energy level. And basically, the way in which we kind of mathematically can write that is you can say that the number of particles with state k, where k is the wave vector, and it's, like we said in the previous video, is quantized in units of pi over L or something, n pi over L, or it might be 2 n pi over L, depending on whether you're taking into account spin. You say that the occupancy of this is either 0, for most of the time it's probably 0 of one individual state, or it's at very rare times actually occupied by one particle. The chances of it being occupied by two particles are minuscule, are very, very, very minuscule. And so you can write that as the kind of average occupancy, which is very close to 0. Like if you think about like a system which is full of available states, think about maybe a stadium, and think about maybe a stadium which has thousands of available spaces. So there's a load and load of states which you can occupy. And then think about 3 people being in the stadium. On average, you're going to find that there's pretty close to 0 people in, like, the average occupancy of a space is nearly 0. So it's about 0. But there will be a first order term, which is non-zero, which would therefore give a slight discrepancy. And that's basically the dilute limit. It's basically saying that the number of states is way more than the number of particles, and so it's really unlikely you're going to have 2 particles in this state. That's pretty much out of the question. So that is the dilute limit. Now, mathematically, you can compare this by comparing 2 different energy scales. Now, I've introduced this idea of the chemical potential. Now, the chemical potential is a bit of a funny concept. It certainly took me a little while to get the hang of, but you can kind of view it sort of as like the water level of a system with regards to its surroundings. So if you have, say, a water level, so if, say, you have like a kind of partition right here, and then you have a water level, let me just draw in highlighting. So you have 2 different sort of water levels. This is a partition right here, and then you have water that's at different levels on either side. Basically, obviously what's going to happen is when you remove this partition, the 2 water levels will even out. So basically you'll end up with a system which looks like that, with a uniform water level and of course no partition. But obviously before there was this partition, and this caused there to be a discrepancy in the different water levels. So it's just like that. Now, chemical potential, you can basically think of it as the potency of a water level to kind of equalize. So this region right here, say it has chemical potential mu1, and this area right here has chemical potential mu2, then the water is obviously going to flow from here to this side. And so we say that mu1 is greater than mu2. The water level on the left is higher than the water level on the right. The chemical potential on the left is higher than the chemical potential on the right. So it's kind of like a sort of measure of how is the system going to diffuse if you leave it to its own devices and you get rid of this partition right here. So, and this is also an important concept for the energy. So the chemical potential is a measure of energy, and basically the dilute limit, I'm not going to go into the full derivation of this, but it can be shown that the dilute limit can mathematically be approximated, or mathematically be stated rather, as the chemical potential. Well, there's 2 conditions. The chemical potential must be very negative, and so it must be less than 0, and the magnitude of the chemical potential has to be much, much greater than the thermal energy of the system. And given those two conditions right there, you find that the ideal gas approximation is held. So how exactly are we going to go from this mathematical approximation to this kind of quantum degenerate state of the system? So how do we get into the quantum regime? Well, let's have a look at the expression for the total number of particles. So if we think about the total number of particles in the system, then we can actually express it as a sum over the states of all of the different average occupancies. So basically what that means is that you can sum over each individual energy state, and you're summing for how many particles there are in that state. So say we have a system like this, a 3-level system to be really, really simple. No particles on here, 1 particle on here, this state, and 2 particles in this state. So say we have that, then we look at this first state and we go, oh no, there's no particles on here on average. By the way, this is the averaged out state. Obviously, in reality, there's going to be a lot of fluctuations, but I'm just simplifying it just to kind of explain what I mean. 1 particle on average in this state, and 2 particles on average in that state. So that's how to get the total number of particles, by summing over the number of states. So this can also be written as the Boltzmann Distribution, which we deduced a few lectures ago, which is this integral between 0 and infinity of the degeneracy, which is the density of states in this case, because we're in the continuous function. We're approximating it as a continuous function. Even though technically it is quantum, it's easier to approximate it as continuous, and then multiplied by this exponential weighting factor, which in the case of 0 chemical potential, I would write E epsilon over kBt. However, the chemical potential can in fact shift this energy, so I will write E minus mu over here. So this is new. I know that in a lot of my previous videos I basically said that the chemical potential was 0 outside. However, this I'm trying to show that for the dilute limit, then you can get some funky thing. If you go away from the dilute limit, then that's basically changing the reference chemical potential. You have to change the chemical potential in order to get to the point where you have a degenerate gas. So there we go, and this is, this is integrated with respect to epsilon. Now for a 3D system, we found that the density of states, not that I can specifically remember it off the top of my head, was proportional to epsilon to the power of 1/2, and that was for a 3D system, which is what we're going to be thinking about, or we could just write that as square root of epsilon, a bit easier. And so if we just kind of turn this into an equation rather than the proportionality relationship, we can get that the rho 3D of epsilon is equal to a constant, which we're just going to call c for now, it doesn't really matter what it's called, multiplied by the square root of epsilon. So let's go ahead and substitute this back into this expression right here. So we're going to get that n is equal, the total number of particles is equal to c, multiplied by the integral between 0 and infinity, root epsilon, multiplied by e to the minus epsilon minus mu over kBt, integrated with respect to epsilon. Now the chemical potential, mu, for the system is in fact a constant. It won't change with respect to energy. And using the laws of exponentials, you can in fact put the mu term of the exponential out the front. So this is using the law of e to the a plus b is equal to e to the a multiplied by e to the b. So let's go ahead and do that. So we're going to get c, this constant right here. We've got an e to the minus mu over kbt. So we're going to get e to the plus mu over kbt multiplied by the integral root epsilon e to the minus epsilon over kbt d epsilon. Okay, now I'm going to make a substitution right here. I'm going to let x equal epsilon over kbt. Now there's a reason why I have done this, that I'm doing this. I know it seems a little bit random at first. And so what I'm now going to do is take dx by d epsilon. Now we can see that that's just going to be a constant, 1 over kbt. And I'm then going to write what d epsilon is in terms of x. So d epsilon is simply kbt dx. Now I'm going to go ahead and substitute, instead of writing epsilon, I'm actually going to write x. I'm going to write this whole integral right here in terms of x. So this is going to be c multiplied by e to the mu over kbt multiplied by the integral between 0 and infinity. This will not change because obviously kbt is just like the constant term. You can see that if x is 0, if epsilon is 0, then x is 0, and if epsilon is infinity, then x is infinity. So you're not going to get any kind of real change right there. And so root epsilon is going to be root kbt times root x, just substituting that in. And we're going to get an e to the minus x from this exponential term. And this is going to be multiplied by kbt times dx. Alright, so let's go ahead and take out all our constant terms out the front of the integral. We're going to get c times e to the mu over kbt. So what are we going to have? We're going to have a kbt, a root kbt, and another kbt. So that's going to combine together to give kbt to the power of 3 over 2. And we're going to have the integral between 0 and infinity of root x times e to the minus x dx. Now, if you notice, there is absolutely nothing in this integral that is physical. It's entirely a mathematical expression. There is actually a mathematical function which was defined by Euler that is called the gamma function. And I don't know if any of you guys have heard of this, but the gamma function is basically, you can kind of think of it as a sort of continuous version of the factorial. So if you think about factorial, if you have 4 factorial, that is 4 times 3 times 2 times 1, which is 24. Now imagine what 3.5 factorial is. It's a bit hard, right? You can't really do 3.5 times every number that's less than 1. So what the gamma function is basically a kind of smoothed out version, a continuous version of the factorial. And you can define the gamma function, I'll write this in a slightly different colour, as the gamma function of z is equal to the integral between 0 and infinity of x to the power of z minus 1 multiplied by e to the minus x integrated with respect to x. So this is actually a function of z rather than a function of x. X is just the thing that you integrate over. And obviously we can see that this kind of looks quite similar to our integral right here. So now we just have to deduce what the gamma function, what this z value is. Now, if we just bear in mind that root x is equal to x to the power of 1/2, then what function would we get that would basically make this equal to x to the power of 1/2? What value of z? And I hope you guys can see that the value z that would make it is 3/2. So z is equal to 3/2 from this formula right here. So if we go ahead and substitute in that, then we can write this integral as c multiplied by, I'm going to put this bit first, kBt to the power of 3/2, multiplied by this exponential e to the mu over kBt, and just the gamma function of 3/2. Now, this gamma function is literally just a number. Now in this case, this number actually happens to be root pi divided by 2. So it's actually got quite a nice simple mathematical expression, but let's go ahead and actually substitute in for this constant value. And then the reason I'm doing this is so that we can actually define some kind of distance scale which we can actually use to see actually how we get to this quantum regime of gases. Because obviously quantum is kind of almost defined by the fact that it's at really, really small distance scales. And so we're actually going to arrive at a quantity which is going to be really, really useful to help us understand that. So the constant c is just the density of states constant, and it's of course dependent on the number of dimensions, the size of the system, and yeah, not much else, the mass of the particle, just the kind of constant stuff. We're going to go ahead and instead of c, we're going to write 4 pi root 2 over 2 pi h bar, all cubed, multiplied by mass to the power of 3/2, multiplied by the volume of the system. So that's all our constant stuff. We're going to get kBt to the power of 3/2, e to the mu over kBt, multiplied by root pi divided by 2. So that is our total number of particles. Okay, I've just gone and simplified it a little bit more so that it's not quite all of the 2's and pi's are a little bit more organised. Now what we're going to do is we're going to rearrange this formula for this term right here. So e to the power of mu over kBt. Let's go ahead and multiply out the denominator. So we're going to get n times 2 root 2 pi to the 3/2 h bar cubed m to the 3/2. Wait, sorry, not the m over 3/2. So that's going to be all that, and this is all going to be divided by all this stuff right here. So we're going to get divided by m to the 3/2 times v times kBt to the power of 3/2. So what we can actually do is, just to tidy it up, we're going to get an n over v. So this bit's quite important, group the number of particles to the volume, and we're going to get, well, 2 root 2 is root 2 to the power of 3/2. So we're going to have a root 2 pi h bar squared divided by m kBt, and all this is going to be raised to the power of 3/2. So that is e to the mu over kBt. And what we're finally going to do is we're going to take the logarithm, the natural logarithm of both sides. So we're going to have ln of e to the mu over kBt. I'm not even going to write that out because I hope you guys can all see that that is just going to be mu over kBt is equal to the log of n over v multiplied by root 2 pi h bar squared over m kBt to the power of 3 over 2. There we go, we have an expression for mu over kBt. Now, if we remember what we said earlier, then we basically want mu over kBt to be really, really, really negative. So we want this to be much, much less than 0, and we want it big. So we want it negative and big. So that basically means, how are we going to get this, this term negative and big? Well, if we have a look at this side, then we basically want this term right here to be very, very small. By very small, I mean small in magnitude. If we remember the graph for what log x looks like, so we get something a bit like this. So it's really, really small and negative, and then it crosses the axis, and then it goes kind of a bit like that. That's a graph of log x versus x. And to get negative and big, we basically we require that the logarithm, the argument of the log, must be very, very, very small, very close to 0. Obviously, log of 0 itself is negative infinity, but we basically want to be in this kind of regime here on the log graph. So, how are we going to get this argument small? Well, let's go ahead and pick it apart. So n over v root 2 pi h bar squared over mkbt to the power of 3 over 2. So this is going to be really, really close to 0. So what can we kind of tweak and change? Well, obviously there's a bunch of stuff in here that's pretty fixed. Most of it's in this bracket, apart from the temperature right there. And so we can see that if we're at a kind of typical room temperature, so not a particularly small temperature, so say like 300 Kelvin or so, then we can see that if we have a really, really low particle density, so if n over v is really small, then basically we can hit this regime, which is the dilute limit. But what I also said was that earlier we can define things in terms of distances. You think about the kind of interparticle distance right here. So let's go ahead and call this d, which is the interparticle distance. Now, obviously, if the interparticle distance is pretty big, then we get the sort of the dilute limit. But we can also define another quantity which is related to the temperature, and that can be related, and this is called what's called the thermal wavelength of a particle. Now, I'm sure you guys are familiar with the concept of the de Broglie wavelength. So what you basically can say is that P is equal to H over lambda, which is the formula for the de Broglie wavelength. So it's just the proportionality constant is, of course, Planck's constant, and so they're related in that pretty simple manner. The typical particle momentum, which we've kind of shown before, of a classical ideal gas, is sort of on the order of kBt. This is the thermal energy, which we have shown previously. So that's kind of the scale in which we're going to be considering. So that's the energy of the particle, the energy thermal. Now we can express the energy in terms of the momentum simply by recalling the formula of kinetic energy and then just putting it in terms of momentum. So E is equal to P squared over 2m. And we can say that this energy is equal to kBt. We can actually set it. Obviously it's not going to be quite exact, but it's kind of on the same order as, so for kind of ideal gas thermal properties, you can say that P squared over 2m is about the same as kBt. And so if we combine this formula together, so P is equal to H over lambda, we can then swap this P squared out for H squared over lambda squared. So we're going to get H squared. This is not Planck's reduced constant, but Planck's kind of full constant over 2m lambda squared is equal to kBt. Now this lambda right here, as a function of temperature, we actually call it the thermal wavelength. In reality, it is just the same as the de Broglie wavelength, but we just have a special name for it. It's called the thermal wavelength. And so if we rearrange this for lambda, we get that lambda is about 2 pi h bar. This is just expanding this term right here, Planck's full constant, divided by the square root of 2m kBt, just by rearranging. So that is our thermal wavelength, and as we can see, the thermal wavelength is proportional to the inverse square root of temperature. So as we can see, if the temperature goes down significantly, then we end up with a situation in which the thermal wavelength actually increases. And the interesting question is, what happens when the thermal wavelength, so if we have a particle, de Broglie of course said we can express it in terms of a wave, what happens when this thermal wavelength starts kind of overlapping with the particle distance? So here's our interparticle distance d right here, and here is our thermal wavelength lambda. What's going to happen? And of course we get some quite interesting effects when this kind of starts to happen. Obviously in the dilute limit, we have said of course before that we want this equation to be negative and big. And so this requires that the interparticle distance, which is related to this term right here, n over v, which is actually, I should kind of finish this off and maybe say that this n divided by v is actually the interparticle distance cubed, or 1 over the interparticle distance cubed. And this 2 pi h bar squared over m kBt is actually the thermal wavelength squared, but then it's raised to the power of 3 over 2, so that is just equal to lambda cubed over d cubed. Maybe multiplied by some pi's and 2's, but we're not too worried about that. So basically this log term is kind of comparing the thermal wavelength to the interparticle distance, and for the ideal gas, this term is very, very small, so as to reconcile mu over kBt, the condition needed right there. But that's of course for the classical case. Now what happens with the quantum case, because that's where things start to get a little more interesting. And this is when the thermal wavelength starts to become comparable with the distance between, the average distance between the particles themselves. And so this is when we start to head towards degenerate quantum gases. So basically, you can kind of get there in two ways. The first thing to do is to basically look at the temperature and then decrease it so that thermal wavelength increases, because you found that if you decrease temperature, the thermal wavelength will increase because of this relation right here. But also you can kind of squeeze the particles together, so you affect this d term right here. And if d becomes really, really small, then you basically get to a point where they are on the same kind of order of magnitude as the thermal wavelength. And in fact, that's actually what happens inside stars, and the tremendous pressures from the gravitational forces within stars cause the particles to become on the same order as the thermal wavelength. And that is basically when we enter the quantum regime, and this is when the statistics start to get a little bit more funky, and that is going to be what we're going to be exploring in the next video. Alright, so next time in this series of videos on statistical physics, we will be looking at how to count quantum statistical particles. We're going to be using Pauli's exclusion principle and seeing how that can lead to two very distinctive types of quantum particle. the fermions and the bosons, and those are kind of really the two types of particle throughout the whole universe, really. Everything is all matter, all particles are divided into fermions and bosons, but the way in which they all come together is the interesting bit, and that's what leads to some very different physics manifested. And then we'll go on to talk about things like superfluids and black body radiation, like all the kind of cool observable stuff that we see in the universe. So hope you guys enjoyed. Hope that was informative. And yeah, see you guys in the next video.